There are two ways to learn a language like Mathematica. You can study solved problems, or you can study features of the language in isolation. This video takes the second approach. Here I will present the features of Mathematica most commonly used in solving problems in science and engineering, organized by topic. So this video and the associated notebook thereby serve as an advertisement of Mathematica's capabilities and a reference on how they're used. Mathematica's full capabilities are vast, but fortunately even users with limited knowledge of its features can use Mathematica very effectively. In the next, third video in this series, I will present solved problems taken from our introductory level course in Math Methods, which teaches the essential features of Mathematica that are most helpful in our core courses. And in the fourth and final video, I will present more advanced examples that could be used in our upper level thermodynamics, transport, and kinetics courses. But Mathematica has substantial capabilities to do calculus symbolically, to do algebra. And so, for example, if you want to integrate a function, you can use integrate. And here I will integrate log x. So I execute this line and I get the answer. If I need to do a definite integral, then one supplies a range for the integration variable. So here integrating a Gaussian over the entire axis, which gives the square root of pi. For functions that cannot be integrated analytically, there is numerical integration available, which is the function n integrate. And so here I integrate e to the minus x cubed, which is not integral in closed form, from 0 to 1 numerically. Mathematica can take derivatives analytically. So here we take the derivative of x log x, or let's make this x log x minus x, and that recovers, of course, the thing that we integrated to get this result. To take a second derivative, you specify the variable you're taking a derivative with respect to and how many times in a little list here. And so that gives the derivative of log x, which is 1 over x. If you have a function of more than one variable, then you can take a partial derivative by specifying the x and it won't touch the y. So here we take the derivative of a Gaussian with respect to x. Mathematica has the capability of doing algebraic solution of equations that can be solved. So here, for example, one can solve the quadratic formula and find the two expected roots. It can also solve simultaneous equations in which the first argument to solve is a list of the equations to be solved. Notice this symbol here, which doesn't look quite like an equal sign, and that's made by typing two equals next to each other, so equals equals, and it shrinks down to this double equal symbol. That's how equations are written, as opposed to the way that variables are assigned. So solving the two equations for x and y, here is a list of the variables that is being solved for, gives the analytical solution. When equations cannot be solved analytically, one wants to find roots to the equations anyway, numerically, and Mathematica provides a nice function for that called find root. So when finding the solution to equations, it's often helpful to make a plot so that you can see what's going on. So here I plot sine x and x over 20 over a certain range, and we can see that there are several places where those two functions are equal. So if I expect to find the root, I'm going to need to give some sort of initial guess that will tell find root what root it is supposed to home in on. It is using a numerical method, something like Newton's method, to find these roots. And so the answer is going to depend on the initial guess. If I guess around 7, then I will get this root here. And if I guess around 2, I'll get this root here. Again, the equation is written with a double equals, and the specification here is of the variable you're looking for and the initial guess written in a little list like this with curly brackets. Find root can solve simultaneous equations. Here I make a plot to show a circle and the exponential function, and so the exponential function crosses the unit circle at 2 points, 0, 1 trivially, and then this point over here. And if I want to find that point, then I want to solve the two equations, x squared plus y squared is 1, and also y is e to the x, and I want to make a guess around x equals minus 1 and y equals 0. And so if I do that, I get this root over there. The answer given by find root comes in the form of a list of substitution rules. That is, x goes to minus 0.9 blah blah blah, y goes to 0.399 blah blah blah. And that's a general way that Mathematica gives the answer from things that involve analytical or numerical solutions. To use those rules, those substitution rules, we use this little operation called slash dot, which is read as substituted by, like this. So the answer that I saved for the sign of x equal x over 20 example was this. And so if I substitute by that substitution rule into these two expressions, I should discover that they're equal. And indeed, I get the same number for both of them. Mathematica has capabilities for optimizing functions, finding minima numerically, and that can be done more generally than these examples show. For example, you can minimize a function of more than one variable. If I plot the decaying oscillation e to the minus x over 5 sine x, I can see that it has several minima, and which one I get is going to depend on what I guess as an initial guess for that minimization, much as the find root operation did. So if I guess around x equals 10, I should find this value. And if I guess around x equals 5, I should find this value. And so the form of find minimum is the function to be minimized, and then a little list which says what variable I'm looking for and what the initial guess is. And what comes back is a list of first the value of the minimum and then a substitution rule of where that minimum is. Mathematica also has the capability of solving linear programming problems. In other words, the optimization of a linear function with linear inequality constraints. And this is the format for that. Here's the function to be minimized, and here is the set of constraints in this particular case, and here are the variables being looked for, and the implicit assumption that these are non-negative is encoded here. This symbol greater than or equals is typed as greater and equal, and then it will shrink down to the little greater or equals sign. This too gives a list of substitution rules for the two values of the optimum. The main data structure in Mathematica to represent all kinds of complicated objects is a list, enclosed in curly brackets, like curly bracket A, comma B, comma C. This is general because lists can contain anything, including other lists. And so, for example, matrices are represented as lists of lists. You could think of it as lists of the rows of the matrix. Lists can be created in various ways. One way is by explicit assignment by hand. So if I make a list called my list, which is just A, comma B, comma C, it echoes that back because A and B and C have no definition at this point. I can also assign to a list explicitly. So having defined my list, I can define D and E and F by saying curly D, comma E, comma F, close curly is my list. And then if I ask what's D, well, it's A, because that's how the assignment was done. A very useful function called table makes a table of its first argument, which is some function of the index variable, which will vary in some regular fashion. So here I make a table of squares where n will step through the integers 1, 2, 3, 4, 5, and I get back the squares. The index can start at different places and can step by different things. So here I make a table of the sines of angles between 0 and 2 pi stepping by pi over 4. And I can also make multidimensional tables, and this makes a matrix which is defined by the product of the two indices I and j. So it makes a 3 by 3 matrix which has 3 rows. The function table form is just a formatting type function which prints a table like mat in a convenient format so that you can see it a little bit more nicely than you can as a list of curly brackets. Having created lists, you need to be able to extract parts of them. So this list of squares that I called square, if I want the third element of it, I use double square brackets. So this little symbol here is made by typing square, square bracket. Let me do the whole thing over again. Square, square, and then 3, and it automatically shrinks down to that double square bracket thing. And this is the third element, which is the 9. If I use a negative index, I'm counting from the back. So the -2 element is this 16 here. Sometimes we want a range of index values, like for example, the first 3 elements would be 1, semi, 3. And sometimes we just want some of the elements, selected ones, in arbitrary order. So I maybe want the second element and then the first one and then the third one. And so I get the 4 and then the 1 and then the 9. If I have a matrix and I want to access, for example, the ith column, the 2, 4, 6 here, then what I say is all rows the first column, or all rows the second column, or something like that. So all rows the second column will be the 2, 4, 6. If I want a subset of columns, then I can use the same operation of the semis, 1, semi, 2 for the second column, and then I'll get a 2 by 3 matrix, which is missing the third column, which I can see more clearly if I type table form of that. This little symbol of % accesses the last output. That's just a convenience to avoid me typing this in again. Finally, similar to the reordering and choosing of the elements here, I can access certain columns of a matrix in a different order by saying all rows and then a set of the columns, the third one, and then the first one. You can think of lists as just lists, or you can think of them as vectors, in which case you would like to do vector algebra on them. And there are many vector algebra operations that act on lists, including dot products. And so if I define a vector vec, which is just 1, 2, 3, then vec.vec is the dot product, which is 14. There are additionally vector algebra functions for the norm, for the cross product, for the outer product, and other operations like that. If I define a matrix like so, then I can take a matrix dotted into a vector in the way that you would expect, and I can take a matrix times a matrix which gives me another matrix. Oftentimes we want the inverse of a matrix. So here I define a rotation matrix rotating in the plane by pi over 4. The inverse of that will be rotating backwards. And because this is a rotation matrix, it's orthogonal, its transpose is its inverse. So if I transpose the matrix, I get the same thing as the inverse. And such matrices have unit determinant. So if I take their determinant, I get 1. There's a complete set of linear algebra operations. I've only scratched the surface here, and they all act on vectors and matrices without having to refer to the individual elements. These functions all act on the entire matrix at once. Table, which made the table of sign values and the table of squares and so forth, is actually doing a loop. In other words, it's performing what would be called a do loop in a language like Fortran or C. And a way of seeing this is just a simple example here, but this can be useful in a variety of ways. If I set some variable prod for product equal to 1, and then I compute a table in which in each line of the table, prod gets replaced by n times its previous value, well then this is going to compute for me the list of factorials from 1 to 5, which it does. 1 times 2 is 2, 1 times 2 times 3 is 6, times 4 is 24, times 5 is 120, and so forth. So the value of prod is being changed as the table is evaluated. And the table also outputs the value of this line at each step. So it's a little program, in effect, that's being done. To plot a function in Mathematica, one uses plot. And so, for example, if I want to plot sine x from minus 6 pi to 6 pi, then I do this. The form of plot is basically the thing to be plotted, and then the variable that's changing in the plot and the range. This plot has a frame on it and tick marks and so forth, and that's because in my initialization I have set some initializations for the function plot to put on a frame and to change the label style and make the frame black and so forth. And if you don't have that in your initialization, you can do that with set options, which will henceforth make those the options for the plot. Now, if you want to do things like add labels to the axes, or change the color of the line, or change the range of the plot, or many other kinds of options that you might want, those can all be done by setting additional options to the plot. And the form of the option is some keyword goes to whatever the option is. So the plot range gets set from -2 to 2. The plot style gets set to red. That will change the one and only curve here to be red instead of this default color. And then the frame labels, because this is a frame, it's got frame labels, are a list of two strings of characters, x or sine x, and those are enclosed in double quotes. So in changing a plot, you don't use some menu or some wizard or some dialog box to make these changes. You change them by changing options on the plot itself. And in that way, you can read how it was done rather than wonder at how it was done by, hunting in some menu. Sometimes you want to combine different plots. And so, for instance, if I want to combine a plot of the sine x with a plot of x over 20, then one way of doing that is to prepare a second plot and then show it together with the first one. Here I'm using a semicolon both to combine these statements and also to suppress the output from the first one so that I don't see the second plot. You'll notice that the first plot shown is the one that gets to decide things like the plot range and the axis labels and so on. I didn't specify that in the second plot of the line x over 20, and I didn't have to. Mathematica has quite a versatile capability for reading data files, the simplest of which is to read in a table of data. And so to have a table of data to read, I'm going to first write one with export, which is the reverse of this process. So here I make a table again of x and the sign of x, and I export it to a file name, which by default will sit in the same folder where my Mathematica document is sitting. This is the quantity to be exported, and this is the format that I'm exporting it in, which is a table format. There are many formats in which data can be written, but this is the most common one. I realize I've made a mistake. This landed in my home directory, not in the directory next to the Mathematica file, and to make that happen, I type the following. Notebook directory is a function that tells me the path where the notebook actually is. If I export like this, then I will see the data file. And if I open it, I see that it's a long list of pairs of numbers. If I want to read that back in again, then I can import the same file. And again, I need to say that it's in the notebook directory. And this greater than, less than is a thing for sticking two strings together. So together that makes the full path of the file without me having to know what it is. And then I tell it the format of the file or how to interpret it, and that will read the table back in again. To plot data as opposed to a function, we want a function that deals with lists of points rather than a continuous function. So here, just as an example, I am making two tables, basically the same tables I just made, except here x and sine x, x and cosine x. I make those two tables, and then instead of plot, I use list plot. And so if I list plot one of those tables, I get a list of points. I get a plot with points in it. If I would like to connect those with a line just to guide the eye, then I can use the option join goes to true and mesh goes to all, draws the points in addition to the line between them. And so that produces a plot that looks like this. List plot, like plot, can plot multiple sets of data together, just like plot can plot multiple functions together, and you list the multiple sets of points together like that, and then you have a plot that looks like this, where the sine and the cosine data sets are shown together. Mathematica has a convenient function for interpolating tables of data called interpolation, and it by default prepares an interpolating function, basically a numerically defined function with a third order interpolation. You can change the order of the interpolation with an option to the function, but that's what it does by default. And the function so defined can be evaluated, integrated, plotted. You can even take the derivative, although that's not such a great idea with noisy data. It behaves in every way like a numerically defined function. So if I interpolate the table I just made, tab 2, I get back this output saying tab int has been defined as an interpolating function. It tells me the range over which it's defined and even gives me a little picture. Then if I evaluate this thing at 3.4, which was in the range, I get a value. I can integrate it from 0 to 1, and I get a value. And furthermore, I can plot it using plot because it's a function now, not just a table of data. And I get back the cosine that was used to define the table of data in the first place. Mathematica has very convenient and robust data fitting capabilities. Here I'm going to generate some fictitious data which is following the function 1 plus x squared, but I'm adding some noise to it, which I do by adding a random real value which is normally distributed, in other words, a Gaussian distributed with a by default 0 mean and unit variance, and by multiplying this by an appropriate amplitude, I can make this be as noisy or noise-free as I want. So to see that, I make this table first and then I plot it. So it's a noisy parabola. And then I can fit it, doing a linear least squares fit to the following set of functions. So this is basically a second order fit, a second order polynomial fit, because I specified a 1 and an x and an x squared. And so the form of this is linear model fit, the table of data to be fitted, the list of functions to be fitted, and the variable on which those functions depend. And what comes back is what's called a fitted model. So the fitted model can be plotted as a function, but I can also ask it questions. It knows things about itself. Most importantly, it knows the confidence intervals for the fitted parameters, that is the coefficients of these three component functions. And so to get the confidence interval table, you just ask it, tab fit, quotes, parameter confidence interval table, close quotes, and you get this handy little table with the best fit value, the standard error, and the confidence interval for each of those three coefficients. As I said, the fit, called tab fit, can be treated as a function, and here, for example, I plot it and then show the resulting fit against the original data, and you can see that it runs right through the data, of course, as it should. Mathematica can also do nonlinear least squares fit, by nonlinear meaning that the function to be fitted is a nonlinear function of its parameters. And so here I have an example, again fictitious data, of a decaying exponential function to which I have added again some random noise, and so that looks like this. And so here I'm going to fit that data set to this function. I know what it is, so I know how to choose one that will fit nicely. So the form of this nonlinear model fit is the table of data to be fitted, the functional form to be fitted, the list of parameters to be fitted, and the variable on which the function depends. Sometimes, if the fit is sensitive, one needs to make initial guesses for these parameters, which can be done by graphing the function with some sensible choice until a reasonable fit results. And those initial guesses are specified as, instead of A, something like curly bracket A, comma, A0, close curly bracket, and so forth. That's not necessary here. So the nonlinear model fit, I made a mistake because my variable D has a definition, as I can see, because it's black, and I need these to be free of definitions. So to avoid that, I need to clear D, and now I can see that A and B and C and D are all blue, which is what I need them to be. That's the syntax which tells me that those don't have definitions. So now I get a fitted model as I should. If I want to know again about the parameter confidence intervals for that, I can simply ask the fit. And again, I can plot the fit against the data in the same way as I did for the linear least squares fit. It is useful in many contexts to be able to define your own functions in Mathematica, and they can do complicated things, or they can simply be a function that you define for convenience. So we're really only scratching the surface here in showing how one defines functions. Here I'm defining a function called my function, which is this 1 plus x squared, and the syntax is x underscore, which means an argument here in this definition called x, and the colon equals means I am giving you a definition which you should apply when I ask you, not right now. It's different from the assignments that we've been making with an equals, which are immediate assignments. This is a delayed assignment. So if I do that, then I have the function my function, which can now be used like any function in particular, plotted. I can define functions that have more than one argument, like this. And there are many options for defining functions. They can be defined to have default arguments. They can have multiple definitions depending on particular choices of the argument or ranges of the argument and so forth. And these examples here just really scratch the surface of that. In conjunction with defining functions, there is a function called module, which serves the purpose in Mathematica that a subroutine would serve in a procedural language like C or Fortran. And the subroutine in those languages gives you local variables that are not accessible to the program that called the subroutine. Here we're just giving a very simple example of this function called find amplitude, which numerically solves an ODE for a damped oscillator, and then computes the function value, well, defines a function based on the solution it finds, and then computes the value of the function at the end of the range, therefore computing the amplitude of the oscillator at that time 10. This module doesn't have any local variables. It's very simple, but what it does do is have 3 lines of code inside of it and separated by semicolons until the last line, and what the module returns as the function value is what the last line evaluates to. So if I define the function by executing the line, and then I do find amplitude at, say, a frequency of 1 and a damping of 0.1, then I get a numerical value. So I've defined a function using module that does a job that requires several lines to express, and this is just sort of scratching the surface of how one might use module. A useful technique in Mathematica for defining functions is to define them in terms of the behavior of find root. So for example, here I have a plot of 2 functions, 50 minus 10x and e to the x squared, and there's an intersection point. That is not a solvable problem. That is, what that intersection point is as a function of the slope is not something I can do the algebra of. Nonetheless, there's implicitly a function which is, if you tell me what b, this slope, is, then I will tell you what this intersection point is. And you might like to have a function that does that. So you can do that by defining a function that's based on the result of find root. So here the x function, meaning tells you this x value as a function of this slope, is defined as x substituted by the result of the find root. And so effectively, I've defined the function x intersection or x function of b numerically in terms of the result of find root. So if I evaluate this function to define it, then I can compute the value for a slope of 4, and it's 1.93, or for a slope of 10 as we have here, and it's 1.8 something. And I can even plot that function and find out how does this intersection point vary as the slope of that line varies. And so that's a very useful technique, using find root in conjunction with a function definition to define effectively an inverse function. Mathematica has strong capabilities for solving differential equations, both analytically, when they can be solved analytically, and numerically, with 2 functions called dsolve and ndsolve. Differential equations is a huge subject, and Mathematica can't do everything, but it can readily handle a wide range of differential equations which occur over and over again. So single or coupled ODEs, which can be linear or nonlinear, of first or higher order. So anything to do with kinetics, for example, anything to do with oscillators. It can solve boundary value problems, meaning elliptic differential equations, in 1 or 2 dimensions on rectangular domains. And with that, you can do problems with cylindrical symmetry, spherical symmetry, and so on. It can solve time-dependent PDEs in 1 space plus 1 time dimension, and that covers a wide range of possibilities also. What it can't do is to solve things that have complicated shapes of the domains. It doesn't do finite element methods. It doesn't do meshing, so it can't solve PDEs on funny-looking shapes. For that, you need a different kind of application, much more specialized. Here, I'm going to demonstrate just a couple of simple examples of how the dsolve and ndsolve look. So, for example, here I've got written out as a set of coupled first-order equations, the equations for an oscillator, the position x, the velocity v. And so this is a damped oscillator with a damping coefficient g, a spring constant k, a mass m, initial position x equals 1, the particles at rest v equals 0. So that's a list of equations and initial conditions, all expressed with double equals. Everywhere the functions x and v appear, they appear with arguments. This is the list of functions to be solved. That is the variable on which they depend. And so I am going to solve this. And you get a fairly fancy looking analytical solution. What I had typed here is after the fact, that is putting a function at the tail end of this thing with this / called postfix notation and saying, please simplify this for me. And it did a slight amount of algebraic simplification. The solution comes out once again as a list of one solution, and that solution is a list of substitution rules for v and x. To access the solution, as for find root, we use this / substituted by. So the x function is defined to be x of t substituted by this rule, and then, having done that, I can then plot that function, which I further need to substitute for what g and m and k are, which I do inside the plot here with another one of these / things. So this is this function substituted by g going to 0.1, m going to 1, k going to 1, and now I can plot the thing and I get a decaying oscillation. In similar fashion, ndsolve works almost the same way. It's got a list of the equations and initial conditions, a list of the functions that you're trying to calculate, but instead of the variable on which the functions depend just being given by itself, you need to specify a range over which the equations will be numerically integrated. And so here I've made a nonlinear oscillator because here the frequency, the spring constant, is depending on the amplitude. So it's not a constant here. The spring constant is bigger when the amplitude is bigger. So the spring is nonlinear and stiffer when it is displaced. Nonetheless, we can solve this with ndsolve, the n standing for numerical. And what comes out of that is a list of one solution, which is a list of substitution rules in terms of interpolating functions, which are defined off of the mesh of the computed values. Once again, to extract those solutions, we use this / substituted by notation. This defines a function, which I can then plot. And here I'm just showing what it looks like compared to the previous solution, which was for the same damping coefficient, but without this nonlinearity. And so with the nonlinearity, the oscillator oscillates faster earlier on, which makes it get ahead of the red curve, gets ahead of the blue curve. Finally, one useful capability that Mathematica has for exploring the behavior of solutions is the set of functions manipulate and animate. And so what manipulate allows you to do is to change a parameter in a calculation with a little slider and to see how the result, typically plotted result, changes. So here, the manipulate command has 3 lines in it, which is first to calculate a solution like we had before with a damping coefficient g and a nonlinearity parameter c, and then to define a function off of that solution, and then to plot that. And that is the last thing in this list of commands, and therefore the thing that will show up, okay? And then what follows is a specification of the slider for g and the slider for c. So the g slider goes from 0 to 1, the c slider goes from 0 to 2, the default value for the g slider is 0.1, the default value for the c slider is 1. So if we execute that, we get this panel here, which, as I slide the G slider around, I can see what happens as I increase the damping, which is the oscillator doesn't oscillate for very long, or I can see what happens if I increase the nonlinearity parameter, and you can see it runs faster at earlier times. If I click down this little plus sign, I can see what value of G I've actually set, and I can actually even see what happens as the G marches through the range in an automatic way. A similar function is animate, which is designed to always animate the result, so the contents are very similar. Here I've just left out the nonlinearity parameter on the spring constant, but kept the damping coefficient varying, and so the specification is exactly as before, now with the damping coefficient, again ranging from 0 to 1 with a starting point of 0.1, and if I press play on that, I get the animation. So it's a simpler form, really, than manipulate. But very nice for showing the way that, that the result of some calculation depends on parameters. Finally, sometimes what you have is a list of plots, so basically a flip book in which some parameter has changed in a systematic way based on some numerical calculation you've done, and you'd like to see what that flip book looks like as you flip through the pages one after the other. So here I've made a table of plots. So plot table is literally a list of plots, and in this list of plots, the frequency of sine x is being systematically increased. And then I use list animate to see what that table looks like. And of course, as the frequency goes up, the frequency in the plot goes up and the sine wiggles faster and faster. So after having surveyed some of the main features of Mathematica as a language, I want to make some final remarks comparing Mathematica to other programming languages that you may be familiar with. So, first of all, Mathematica is text-based almost entirely, not menu-driven. So in strong contrast, for example, to something like Excel, where to do very many things you're using menus and dialog boxes and wizards and so forth. In Mathematica, the inputs that produced the results in the notebook are all completely visible. Everything is text-based. Mathematica is interpreted, not compiled. So in this respect, it's like Python. You can type in a line and execute it, and if you don't quite like what you got, you can change it again and execute it again. It's not compiled. It's not like C. You don't have a cycle of compile and execute that slows down the process of finding out whether your idea is correct. It has analytical, numerical, and graphical capabilities, and in this regard, it is unique among mathematical toolboxes in combining all three of these in one application. Because it's a commercial package, it has extensive built-in help with examples and tutorials, in contrast, for example, to Python, which is open source and therefore has no inbuilt help. It's based on functions, not procedures. That is, the basic metaphor is functions transform data and produce outputs. It does, however, have procedural functions, do and for and if and so forth, and so you can write programs that look procedural. But if you are doing that very much, it probably means you're not using the capabilities of Mathematica to avoid that kind of thing and to work at the highest level of the language possible. And this is a virtue because the fewer details that you are keeping track of, the fewer chances you have to make a mistake. If you're constantly accessing the elements of some list and looping over things, you're probably doing it wrong. Mathematica functions, the arguments are passed by value, not by reference. That is, functions can't change their arguments. That's meant to protect you from yourself. Functions can change global variables, and they can have, if you use module, local variables that are untouchable by the outside world, and in this way, local and global variables are protected. Mathematica is a very high-level language. It has many, many functions that act on big objects at once and do big things without having to loop. And this means that you can do an awful lot with only a few lines of code. And this is a great virtue because it's a truism in programming that the number of errors per line of code is a constant independent of the language. So you'd like your programs to be as short as possible with you having to deal with and therefore possibly mess up as few details as possible. Mathematica has a huge number of built-in functions, and this might at first sight seem daunting, but it is the case that you can do very much with only the most common few functions. You don't have to have encyclopedic knowledge of the language in order to use it effectively. Mathematica has rational conventions for naming things. The built-in names are all either traditional mathematical symbol names like exp and sine and cos, or they're capitalized English words or combinations of them, not inscrutable abbreviations. Variables, like in Python, are typeless and undeclared. In other words, you don't have to say, this will be a matrix, this will be a vector of length 5, this will be a complex number. You just start using them and assigning things to them. And variables can hold more or less anything. For example, they can hold a plot, or they can hold a list of a list of a list, or they can hold an entire table of data, or what have you. The data structures in Mathematica are deceptively simple. They are lists and strings of characters, which I have not focused on very much in this tutorial because it's of less importance in solving problems in science and engineering. Lists are a very versatile data set because you can have lists of lists of lists and lists of all kinds of things. And so I've never encountered a situation where I felt I needed some more structured thing in Mathematica than a list to store my values. The syntax of Mathematica is relatively simple, but one important thing to remember is that there are 4 different kinds of brackets. Square brackets for function arguments, curly brackets for list, double square brackets for the indices that allow you to take parts of lists, and parentheses for algebraic grouping.